So, uncertainty probability. So, do people all up on their probability theory? Seems like quite a few people are up here, like they remember the high school prob stuff. It's the type of stuff that you forget. I work at this stuff and I forget it all the time. It's kind of just normal. So when we go to Bayesian networks, because Bayesian networks are good for handling systems with uncertainties. There's uncertainties in a lot of different things here. We've got different types of uncertainty that we might be interested in. There might be ignorance. We just might not know about the world. I might flip a coin, and before I look at it, I just don't know what's there. There can be complexity, such as in the human brain or in an ecological system. And we have an uncertainty about how that system actually works. Physical randomness, we just don't know what's going to happen with that coin when it's properly modelling the coin when it's flipping around, and vagueness as well. So Bayesian networks are good for ignorance, complexity and physical randomness, but vagueness is something that we need to be careful about. So often when we start doing Bayesian networks, people will start thinking with these vague type problems, and you might actually end up accidentally putting in sort of vague node variables in there. So you need to be careful about that. We can go to fuzzy logic systems and stuff like that, which I forget people's names. God, what was your name? Well, you've done work with the fuzzy logic stuff, haven't you? So we can go to that fuzzy logic stuff for this, but that's not going to be a problem with this project, I understand.
Well, we're not planning to include the fuzzy stuff, but the vagueness is going to be a problem in the sense that people will need to clarify the definitions of variables.
Yeah.
So in other words, you need to avoid the problem.
So I suppose with this particular project, we need to be very careful about identifying when this is a vague problem and not trying to use a Bayesian network to handle that type of as a solution for that.
Like if you just you want to have a variable in your system, then you need to be very careful. There'll be an attached definition where you need to clarify what it means.
Exactly. Okay, so probability calculus. So this was like high school probability stuff. Now, we had all these guys here who were sending letters to each other and working out how to handle probability, and this was mostly about how they could do gambling problems, I believe. And they came up with these axioms of probability. So generally we write a whole lot of mathematics up, and it looks really quite cryptic and difficult, but it's really quite simple. So these are the base axioms of probability. So the probability of some type of event happening is going to be 1. So if I have a 6-sided dice, the probability it's going to be either a 1, a 2, or 3, or 4, or 5, or a 6 is going to be 1. So the entire event space is probability of 1. Any individual event within that probability space is at least 0. You can't have a negative probability. So probability is bounded between 0 and 1. That's pretty straightforward and simple. And we all remember that from high school, I'm guessing. And then the other one, which is the slightly more difficult but not really that big, is the additivity one. So the probability of two incompatible events, either of them happening, is just the sum of the probabilities. So the probability of a 1 coming up on my dice is 1 in 6. The probability of 2 coming up on my dice is 1 in 6. The probability of a 1 or 2 coming up is going to be 1 plus 1 over 6. So we just add those probabilities together. Now from this and a whole lot of mathematical proof type stuff that Eric likes doing, I think, we can come up with all the rest of the rules about probability. So one that's particularly, we have our little Venn diagram thingy here. People remember Venn diagrams, don't they? I'll come back to that later. So one that's particularly useful and interesting for Bayesian networks is the conditional probability here. So we have our mathematical notation here, which you need to read here. So we read this as the probability of some event x, given that we know that y has happened, is this thing here. So that's a probability of x and y happening divided by the probability of the y event happening. Looks a bit difficult with the mathematics stuff, so we go to the Venn diagram thing to sort of explain this. So we have our event space here. I feel like I'm going to am I safe with this?
Yeah.
I might just move this chair out of the way. So I can get a bit hand wavy when I'm presenting. Okay, so we've got some event space here. We've got this x and we've got this y. And there's some point here where these two events actually overlap with each other. I'm going to hang myself. Okay, so what happens here is when we're looking at this conditional probability, so this is x given that we know that y has happened. So when we do that, our new sort of probability space that y has happened, we know we're somewhere in this y circle here. So if we want to know what the probability of x happening, given that we're in this y space, it's this intersection area here. So what we're looking at is the ratio of this overlap area to the whole of y here, which gives us this number up here. Now, I don't know how much you guys are going to be actually using this stuff when you actually, because we have our Bayesian network software to actually generate all these numbers and do all these numbers for us, but it's good to have some background understanding about it. Independence. So we have this important thing about independence here. So we read this. This is our notation for independence. So x and y is independent of y if is the case that x given y is the same as the probability of x by itself. So that's basically, well, this is these types of situations where we have these gambling devices. We often will think that if we know I've had a streak of reds coming up on the roulette wheel, then our probability of black is going to have a higher probability, but that's actually a fallacy. We know that they're independent of each other. So basically the way that we read this is that two variables are independent of each other if learning about one of them doesn't tell us about another one at all. So we have an example of a dependent relationship here. So the probability that we're going to see a rainbow, given that we know that it's raining out there, is going to be greater than our probability of seeing a rainbow without knowing anything. So knowing that there's rain going on will increase our chance of a rainbow, a belief of seeing a rainbow. And we have, like, if it's not independent, then it's dependent, and vice versa. So then we go to this probability terminology. So we have propositions, and propositions can either be true or false. So, for example, in this one, our proposition here is the crop yield is high, and we have some strict definition about what a high is. Maybe that's a certain dollar value or something like that. We know that's either going to be true or false. It's either going to be high or it's not going to be high. Before we go and look, or if we're thinking about the future or something like that, then we'll have some uncertainty about that. So we'll have a degree of belief, and that's where we bring in our probability. So we bring in some probability between 0 and 1 that we believe about that thing. So the probability this crop yield is going to be high in this next year is going to be 10% or 0.1. Now we call this our prior probability. So before we know anything else about the world, what's our initial probability that we're going to put to this event? From that we can go on to our conditional probability, which gives us talk about the impact of evidence, right? So we know that the crop yield is going to be affected by the rainfall for the next year. So we've got a forecast for the rainfall for the year. And if it's going to be above average, then our probability of crop yield is going to go up. So in this case, we've gone up from 0.1 to 0.5. This we call our conditional probability or posterior probability if we're using Bayesian.
Can I interject there? So Anne was saying the same thing, and that's actually, I was going to correct her on that. But, so prior means before.
Right.
So prior is before you learn something, and then posterior is after. So that's after the new probability after you learn something. Whereas the unconditional probability, or is without a specific value for the other variable, and the conditional probability, certainly with an ordinary condition, is the new probability once you know a specific value for the variable. And as Owen said, it's usually that the probability you had before is the average one where you don't know the value, and then you learn a value, and then that becomes the posterior after. This is not always the case. So, for example, if you thought that a variable had a certain value, and then you learned that you were wrong, or that in this context it doesn't always have that value, then you would be going from a conditional to some sort of an unconditional probability. So right. It's possible to go in the other direction. So prior is what you have before, and posterior is what you have after, and then unconditional is when you don't know the values of the relevant variables, and conditional is when you do know the values of some other relevant variables.
Okay.
So they are actually different concepts, and I'm going to inject that.
Yeah, cool. Yeah. Well, thank you. Okay, so we've got our probability calculus here. Now, so the hero of Bayesian networks is Reverend Thomas Bayes. As was the case back in the 1700s, a lot of people who were working in mathematics and science were actually a part of the clergy as well, so he was a reverend here. And he came up with this neat little formula that was the heart of Bayesian networks. Again, we got this kind of mathematical thing. So have people seen this before? Yeah. Do you know how to read it? I'm going to read it for you anyway, just in case. So we've got this H is a hypothesis, some belief about the world, like proposition, and E is evidence here. So it says that our probability of a hypothesis, given that we've observed some evidence about the world, is equal to this thing over here. So it's a probability of the evidence given the hypothesis, the probability of the hypothesis, our prior probability, and the probability of the evidence there. And then we have this conditionalization idea here, that as we have our prior probability of a hypothesis, and as we get evidence, we get a new prior belief. I don't know if I'm being abusive of my terminology there, Eric. Does that sound right with the conditionalization? You have been told. Okay, so we have this posterior probability. So probability of the hypothesis given the evidence is going to be equal to the likelihood of that evidence times the prior divided by the probability of the evidence altogether. And we're going to sort of play around with this and do some examples and see how this works. So I think this is actually relevant because it's not in your printed notes, but I'm going to shut your notes or not look at them for a little bit. So think about this example, right? So somebody's come and we're in a cancer clinic, and somebody's walked in the street and they think that they might have cancer. Now we know some things about this clinic here, that 1 in 100 people who walk into this cancer clinic actually do have cancer. So that's our prior probability here. We can do a test, and we know our false positives and true positive rates for that test here. So in this case, for this test that we can run, our true positive rate, so the probability that we're going to get a positive result given that they actually have cancer, is 80%. Our false positive rate, that's the probability that they will get a positive result if they don't have cancer, is 10%. 1% or 10%? Sorry?
10% or 1%?
10%. So our prior is 1% and this is 10%. Sorry, I should be the same 0.1 probability. So at this point here, I just kind of want people to sort of think about, so you think you're just walked into this cancer clinic and you've got a positive test result. How worried are you? What do we think your probability is that you actually do have cancer? So I want you to have a think about what you think the new belief is going to be.
50%.
Yeah, you got 50%? Anybody else want to offer something? Who thinks it's going to be something like, I don't know, 50%? Anybody think it's going to be greater than 50% probability? Maybe greater? So maybe 70%, 80%? Who thinks that? What about less? So maybe 20, 30%? 20?
10.
10, yeah. Anybody less than 10? Anybody think less than 10%? No, I mean, you're right to be cautious because it's obviously a trap. The point is that we're trying to demonstrate that people aren't very good with this. We do the mathematics of this, and the chance that you've actually got cancer given you've got a positive test result in this situation is only 7%. So we've got less than 10% there. Now that's a big increase because we went from like 1% to 7 or 7.5% there. So it's definitely cause for concern, and we might go and do a different test there, but we're not going to start calling all our friends and family and telling them that we're going to die of cancer yet. It's motivation to do more. So that's when we plug this all into our little Bayes theorem stuff here. And a nice intuitive way to sort of understand this type of thing is to use these frequency formats here. So imagine a population of 1,000 people coming in here. We know that 10% of these, or so 1% of them, have cancer. So 10 out of that 1,000 people will actually have cancer. Of that 10% of those, we have this 80% true positive. So they have cancer, they get a positive result there. So we've got this 8 here. And then the rest go over here. The rest of them all come into the not cancer category. And we have the false positive rate of 10%, which is coming in here. And the rest go into here. Now when we know, so we're in the situation where we know we've got a positive test result, so we can ignore these two ones here and we just look at these types of things here. So we can see that we're far more likely to not have cancer and get a false positive than have cancer and have a true positive rate here. So we look at the ratio of this 8 between these two numbers, and that's what's basically over here, this one over here. So we've got the 0.8 is that one, and the 0.8 and 0.9. Okay, so we have an exercise. If you flick back in your book, so this is a pen and paper exercise. It should be fairly... So we want to look for this page here. So it's about 3/4 of the way through, 2/3 of the way through. And what I want you to do is actually look at this example and do it yourself and try out the mathematics. So if you just go right to the end of the slides and then you get to the exercise section. Okay, so our problem is here we've got some Olympic runner that we're testing for the presence of steroids. We have some statistics here that we know a prior probability, what's our prior belief that somebody's athlete's going to be using steroids, and we also have these true positives, false positives for the test result as well. So what I want you to do is do your little pen and paper exercise and work out the probability. What's your new belief for the athlete actually having used steroids? Anybody want to volunteer an answer? I kind of had a look around the room. I think everybody pretty much got it right.
324.
334?
324.
324. Anybody else get something different? 324?
1.345.
1345. Okay.
Point
Yeah, I'll yeah. 0.345.
45.
Okay. That's close. So for the first one, I can't remember off the top of my head.
0.324232.
So yeah, I think that's about right here. So I might just quickly go through the exercise just to make sure that everybody was up to speed with it. So this is the way that I handle it. First of all, I write up my Bayes theorem here, and then I do this expansion here, which I often neglect to talk about, which is how we get this probability of evidence. So the probability of evidence is two different worlds here. We got this probability of evidence given the hypothesis, and we can work out what's the chance in this world by doing the prior and that. And then we can do the opposite there to actually expand out the evidence stuff. Then reading through the question, I'll look for these different values here. So we've got our prior probability, which was 1%, 0, 1. And the not prior is 1 minus that, so 0.99. The probability that they didn't use steroids. They did use steroids. Yeah. Our true positive rate was 95%, and our false positive rate was 2% here. So that's what everybody got, yeah? And then when we plug that all in there, then it's just a matter of like making a mistake with the calculator and pushing wrong buttons and stuff like that. So I had the 0.09 times 0.1 over the same thing here, plus 0.02 times 0.99. So everybody got it right. That's pretty much what you did there. And then we all mash our fingers on the calculator and then make some mistake, and we come up with something that's like 3.2, I think it was, 32%. Anybody do the next question? Oh, is it in that? Is it? So part 2 was we just changed it around and we increased the prior, I think that right? Can somebody tell me what it was? What we changed it from? 0.1 to 0.5. So we're changing our numbers here. 9.5 there. And in here. Did I get that right? 5%, yeah. Yeah, people don't see it. It's okay, I didn't tell you to. So we've just changed this, this prior probability here, and this goes up from 32 to something like 70, I think it was 71.
7 something. Yeah.
70, yeah. 71.
So with probability of E given H and the probability of E given not H,
Yeah.
what other possibilities are there?
Well, so we've got this is the true positive and the false positive, and then we've got the false negative and the false
true
true.
positives and other false positives. What else is there?
Well, once we know that we've got a positive case. That's everything that we're interested in. But there's just the 4 different outcomes, which we can have like a true positive, a false positive, a true negative, and a false negative.
So there's 4
But-
outcomes. So the true and false negatives add up to 0.03.
What was it again? I can't remember.
Is
So,
that
so
really-
the false, the true positive and the false negatives add up to 1. Is that right?
Is that right?
Yeah.
Yeah.